let's go, let's go, let's go, let's go.
What's going on, everybody? Welcome on this wonderful Monday to Building Stuff with Nova. This is the place that we like to call your ideation laboratory, your virtual makerspace, if you will, your mastermind. This is a community where we're building together. I am your host, Dr. Nehemiah Mabry, but you know what? You can call me Dr. Nee. I'm perfectly fine with that. Shout out to everybody joining us on Twitch. This is where we typically live, but we also have special guests today on YouTube as well as Facebook. So we just got a nice big party today. And if there was a day to have a nice big party across platforms, it will be today. I'm gonna tell you why, because today we have a special guest. We have a friend of mine who I actually looked up to for a while and had the privilege of meeting just recently, even this year, that's gonna be joining us here in just a little bit. But first, I need to know where you're checking in from. Whether you are here on Twitch, Nova Building Stuff channel, if you are on the Nova YouTube channel, or if you're on the Nova Facebook channel, drop in the chat exactly where you're joining us from. I am joining you right now from the state of North Carolina. Some folks call it North Kakalaki. I don't know where you're at, but I need to see you in the chat. Shout out to everybody that's joining us, whether you're from the first time, or this is the second, or you've been with us for a while. We've been calling the crew, the people that's been hanging out, at least to date, we've been calling it the Building Committee. So shout out to the Building Committee who's been here on Nova Building Stuff. That's our name until further notice. But again, I want to know where you're joining us from, whether or not this is your first time. Again, I'm coming from North Carolina. We already see our good friends Nova in the chat. Shout out to everybody again on YouTube, on Facebook. Nova is coming to us from Boston, right? So we got a nice guest from the home of the NBA World Champions, I believe. Yeah, the NBA World Champions, as they call, but the NBA champions, the Boston Celtics. So shout out to Nova with us. Let's see who else we got. I see D Programmer 9 in the chat. Sup? Good to see you. Welcome to Building Stuff with Nova. Again, at any point, let us know where you're checking in from. We'd love to give you a shout out. As a matter of fact, if you're brand new, this is a perfect time to hit follow if you're on Facebook, follow if you're on Twitch, or subscribe if you're on YouTube. Because this is a place where we continue to give great content. Nova is always known for incredible content. And on this particular show, we're all about engineering. We're all about engineering. We've been doing a lot of cool things. And so we're just happy to have you with us. Let's see what we got in the chat. We got D Programmer 9 again, joining us from Tampa, Florida. Shout out to you down in Florida. We got future doctors in the building representing Tennessee. Good to see you, future doctors. What do we have on the other platforms? Noah, let me know, who do you see? Let's continue to give love as we move forward in this program, because I'm going to be focused here in just a little bit as I bring to you our guests for today. Now, let me catch you up really quick. We have been talking about engineering and a number of topics on this platform. Nova, Building Stuff with Nova. Again, I'm your host, Dr. Nee. Some people look at me as a mentor. Sometimes I'm your mentee if I'm playing a game. We've been doing all of that over on Twitch. Today, across platforms, we're going to be bringing you some ideations and some discussions around the idea of looking beyond the earth. We started off talking about structural engineering, mechanical engineering. We were talking about building bridges. And even last week, we started talking about building rockets. But this person I have today is someone that all of you will enjoy, because I really enjoy you. Let me bring him up really quick. Oh, let me tell you this. We have an agenda too. Let's bring our agenda really quick before I bring my guest on the screen. We have an agenda for the day. It's pretty short and simple, as you can already guess. As I say here on the screen, I'm just welcoming, letting you all know if this is your first time or if this is not your first time. We welcome you here to Building Stuff with Nova. We want to know where you're from. But I'm going to be bringing in our guest, and I'm going to bring up a slide so you can see all about him before you see his face, before you hear his wisdom. He goes by the name of Dr. Hakeem Oluseyi, and that is who we have today. And I promise you that you're going to enjoy this entire conversation as we have sort of a conversation between his background in astrophysics and my background in engineering. I can't wait to do it. As a matter of fact, why wait? Let me show you here on the screen. We have this wonderful intro slide that I want to share with you today. Dr. Hakeem Oluseyi. He is an American astrophysicist, cosmologist, inventor, educator, science communicator, author, actor. He got acting chops too, y'all. Veteran and humanitarian. Oluseyi appears as commentator and scientific authority on shows including How the Universe Works, Outrageous Acts of Science, Curiosity, NASA's Unexplained Files, Space Deepest Secrets, Strips the Cosmos, and much, much more. As a matter of fact, I saw him even on this show called Bacon Impossible, where he was tasting some nice desserts out there. So I need y'all to do me a favor. Shout out to y'all in chat. And of course, everybody that's on YouTube, everybody's on Facebook. We typically live on Twitch, but today we're across platforms. But if you hear me say the word chat, I'm talking about you, chat. I'm talking about everybody that's hanging out with us today. Shout out to you all. Let's get some emotes, just like my friend Maru14 dropping in here. Dropping all these emotes. Let's get some emojis if you're not on Twitch. Let's get some love. Whatever you do in the chat. Chat, I need you to show love as I present to some and introduce to others my good friend who I'm happy to have here on the screen. None other than Dr. Hakeem Oluseyi. Dr. Hakeem, how you doing today, man? Good to see you.
I am doing great. Happy to be here, man. Good to see you as well.
Indeed. Audience. So check this out, man. So
yes.
I tell the building committee, everybody's on here. They showing you love. Shout out to Tori Star. I go by Dr. Nee, and then you go by Dr. O sometimes. That's cool. That's
Dr.
Cool, right?
O, exactly.
Dr. O.
That's my that's my regular name. And when I'm in my like evil superhero costume, I'm Dr. O, so
the evil and
super
intelligent
villain.
And sometimes brilliant, not always evil, right? I'm gonna assume that
No.
Okay.
No. My evil ain't that evil at all.
I got you.
I got good evil.
Well, listen, man, I can tell you something that's good, and that is the love you're getting in the chat across platforms on YouTube, on Facebook. You got the hearts, you got the W's, you got the fire emojis and emotes. You even got the little bitty, which on YouTube, on Twitch. And I'm gonna tell people again, we do this pretty much daily on Twitch, right? And on Twitch, we have a lot of fun, and we've been able to put custom like images and pictures of different things that we turn into things that go into the chat. Man, all that and more is coming to you right now as you have joined us on Building Stuff in Nova. So again, thank you for being here. Thank you for being here.
Thank you, man. Thank you for having me. Thank you for having me. There's another science communicator with energy like me.
Hey,
people always tell me you got so much energy. Scientists are dry and boring.
Well, listen, this conversation is going to be anything but dry and boring. As a matter of fact, when I looked at and I got to just show the people this. When I looked at your illustrious career here, right, on the screen right now, I'm about to show people this incredible CV that really, this is just the tip of the iceberg of. If I'm going to be honest with you, this is the tip of the iceberg of what represents an incredible career of yours. I mean, look, professor, president, chief executive officer, science education manager, fellow, assistant professor, senior process engineer. I mean, the list goes on and on and on. And chat, I want y'all to know, this is literally the tip of the iceberg. And I just want to come back to you really quick and say, man, as it relates to your origin story, one of the things that I've been happy to kind of learn about you before you even get into the technical stuff is that if someone were to go back in your past and take a snapshot of your life at a certain period, you would have been someone that people probably wouldn't have guessed would have had a CV like we just began to kind of like start talking about.
Man, I would not have believed it. I mean, look, man, you're absolutely right. My background had nothing academic in it, nowhere in my family. Now, there was a lot of engineering, home engineering, because my dad is a farmer, basically, right? But, he left and went to the big city. But I lived in Mississippi on the farm. And, back then in the 70s and the 80s, you did everything yourself. You fixed it, you built it, so I've been building stuff for a long time.
Right. But, one of the things I think is really interesting about your story, and as I began to kind of like educate myself, is that you were someone who was very curious and you kind of had this ferocious desire for learning. In fact, you started reading the encyclopedia, I guess, what was that, the age of 10, just to kind of start educating yourself?
Yeah. Right.
Yeah. Tell me about that experience.
My goal was to read in,
What did that land
What's that?
Where did that land?
Well, that landed me. So my idea was to read the encyclopedias from A to Z. And it was going well, but the process got interrupted when I ran into this dude named Albert Einstein in the E volume.
Yeah.
And I just basically had to jump to R and read relativity. And man, I just got stuck. Like, I just got, just obsessed with relativity and Einstein and thought that I would teach it to myself. And, coincidentally, later in high school, my girlfriend gets a TRS-80 color computer.
Yep.
And I used her computer to teach myself the programming language BASIC. And then the following year, my junior year of high school, these professors came to my high school because, we're the poor high school, right? The underperforming high school. They were doing outreach. And they told us about this thing called science fairs. And so I did basically, my science fair project was called Programming Relativity.
Yeah.
And so I basically taught myself all the math by myself, the coding, programmed up all the effects of relativity, and ended up winning first place in the state at the Mississippi State Science Fair in 1985.
Now this is crazy. Chat, I hope y'all heard what he just said. So you not only learned relativity, you were able to code it, basically build a program that basically, I guess, did the effects or demonstrated the effects.
Oh, yeah.
Of relativity?
Demonstrated the effects of time dilation, length contraction, space-time intervals, what we call relativistic mass. But I made it like a game, sort of, right? So, not that gamified, but slightly gamified.
Right.
Yeah,
So, chat, for those who are joining us, this is Building Stuff with Nova. Shout out to everybody in the chat across platforms. We see Star Fox Trinity. Yes. Shout out to, I guess it's one of my schoolmates there in the chat. Good to see you. We got Sir William Thatcher. We have a couple of people. Minor Rule 14. I am here with none other than Dr. Hakeem Oluseyi. And one of the things that I think was pretty dope about what you just shared is that your ability to not only understand, I guess, physics on this scale, but also code it is almost like a microcosm or the beginning of what I feel like this interview is going to be. And that is pretty much a combination of your background in astrophysics, right? And my background as an engineer, because what you were doing at that time, and I think I got like a pretty cool pic here. I'm gonna bring up a pic of a keyboard. You tell me if this looks anything like the thing that you were programming on at all. Does it look like it?
That's the exact one. That's the exact computer.
Are you
from
kidding me?
Anita's mother. No,
Wow.
So when I told her I was writing my memoir in 2018, her mom went in the garage and dug it out and found it. That's why it looked so dirty and crappy. So that was a 2020 photograph of a computer that she got in 1983 or 84 for Christmas. I think 1983.
That's crazy. That's crazy.
Yeah.
But you demonstrated, again, your intelligence, because if anyone goes and does some research on you, which I encourage you all to do, you will see that like his background was anything but pristine, right? If you will, right? But
that's one way of putting it.
You said that's one way of putting it. Well, the thing is, like, you combine the knowledge of science with the knowledge of what was software engineering, right? This was software engineering.
That's right. Yeah, and as I look at how my actual research career developed, I got my first research experience as an undergraduate. I went to the University of Georgia for the summer, and it worked like this. Here is a software. It was called the MM2 program, Molecular Mechanics or something like that.
Right.
Use this program to model these particular clusters and see if it matches what people have done in the laboratory. But get it, here's a program. My next project was at Tougaloo College, and my advisor was like, here are some equations for electron paramagnetic resonance. Take these equations, solve them numerically, and simulate experimental results. Then it became, here's a physics situation happening at the sun. Use the equations of magnetohydrodynamics to model these structures, right? Just think of the sets of differential equations.
Right.
And, I had fifth order coupled nonlinear differential equations. It was like a disaster. Not a disaster,
crazy
but
math.
It was
Crazy
sticky.
work.
Let's say it's sticky, icky. The type of stuff that takes, because we were like a small group. It wasn't like a group of us doing this. It was one at a time.
Right.
Yeah. So it was tight.
Man, that's crazy. And you know what? And by the way, chat, YouTube, Facebook, Twitch, I want y'all to know that you're welcome at any point to ask questions. We may or may not be able to get to them in real time, but we definitely want to get some time to where we can kind of address some of the things that come across your mind as we talk to astrophysicists. And here's a term I heard you use for the first time, star hacker, right? And I'm going to actually break that down, right? Because really, and you kind of already started, but hacking is usually associated with, again, computer engineering, software engineering. We're like hacking codes. Well, you, my friend, the people you all are looking at, chat, is a star hacker. Like, break down that term star hacking a little bit more so people can understand, again, that astrophysics engineering fusion.
So I did my PhD work studying stars, right? And the thing that really just blew my mind is, I had never thought of it this way before. And so I ended up creating a question I feel like every student should be asked in the first grade. And that question is, where does light come from? And the simplest answer to me is matter makes it. Okay. All right. And what I learned, right? And as I learned as an experimental and observational astrophysicist, is that the identity of what the matter is and what it's doing is encoded in the light when it's made, right? And so I am a graduate, like I'm a country boy. I'm from the deep woods of Mississippi. And I'm in graduate school in Silicon Valley. And everybody's talking about Silicon Valley companies. So when school ends, I'm like, oh, I want to know about that. I don't know anything about the corporate world.
Right.
So I go to a Silicon Valley company that make computer chips, makes the tools that makes computer chips, Applied Materials. And it turns out that my knowledge of reading light led to a whole new division for the company and was pioneering in the field of semiconductor manufacturing.
Right.
I basically created the very first in situ process diagnostics and control, so using plasma emissions. So basically the only thing they did is, at the time, they would do what's called endpoint detection. So if you're etching a layer on top of another layer, whatever species you're etching, when you get to the bottom of that layer, you'll see some emission line associated with that particular material take a big drop. Okay. Or once you hit the material under it, you'll see a big rise. But what you couldn't do is say, oh, what is the etch rate? What is the uniformity of the process? Is the pressure in tune? Is the RF power in tune? And I created these diagnostics that just by looking at the plasma light, you can determine what's happening in the chamber and correct it in real time to make sure, instead of testing afterwards to make sure you got it right, you make sure you get it right each time. So each of those patents has over like 200 citations at this point.
Oh yeah, and listen, I didn't even touch on the patents, man, which is really crazy. And maybe I guess I'm assuming that's how an astrophysicist who is known for their study of the universe becomes highly patented. What is it, about 11 patents you have here? How many? I mean, I'm not showing all of them, but you have like 11 patents or something like that?
Yeah, 11 patents. Yeah,
that's crazy.
So several of these are on experimentally using high resistivity, low resistivity metals, tungsten in particular.
Right.
And the other are on the spectroscopic diagnostics and control. So in one case, I developed the processes that allowed the last generation of planar transistors with Moore's law. And the other one was just a completely new realm for semiconductor manufacturing.
Okay. All right. Chat, I hope you all here. We are getting deep into science here together. And as an engineer, I'm going to have to get some of this broken down, because here's what I'm hearing. Here's what I'm hearing, Dr. O. Again, you want to be able to detect plasma light, right? You want to be able to create these things. And so there's a method in which, understanding how the light operates, how it's detected, how it's captured, how it's communicated, I guess even transferred to digital signals and so forth takes place. But still, ultimately, you need to basically tune or optimize or build these engineering components in a way that it actually could jive with or accurately detect the behavior of this scientific phenomena. Is that a good way of saying it?
Yeah, exactly. So there's light being emitted and there's a physical process happening. And so you look at the light and say, oh, here's how I understand this physical process in detail. And then if the process is out of specification, you can dial that sucker into specification. So if you have the slide with the spectra, that's
the light. You mean the light spectra? Or
exactly. So what I did today, you would do using machine learning or something like that. But I basically did it all in my head. I made this big table of here are all the because if you make one change over here, right? Suppose I want to change the pressure in the chamber, and I want to change, say, the spacing between the electrode and my wafer that I'm processing.
Right.
Moving one smaller and one bigger might have the exact same effect on the spectrum. So the question becomes, how do you distinguish between the two? Right. So it's these complex ratios that I created that, this is my solar craft so if you ever look at the pictures of the sun, which has all the plasma loops that you see, I was on the team that pioneered that work. I was a graduate student. We were a team of about 5 students, and our PhD advisor, Art Walker, who you showed. But so every time you see these pictures of the sun with the plasma loops everywhere, think Art Walker and his team. We did that first.
Oh, so let me show, because I don't think our audience saw this. Again, This is building stuff with NOVA, and today we're building stuff, at least our intelligence on this topic, with Dr. Hakeem Oluseyi. This was your graduate school advisor, right?
That's right. Yeah. More than that to me, man. I carried the man's casket. He was like,
Wow.
the father that to me. And, his wife would tell me that I was like the son he wished, he hadn't had. But, I came in a knucklehead, and he taught me to be a scholar and a gentleman, and a very careful experimentalist. But this dude pioneered a lot of things. Like, he pioneered X-ray astrophysics, basically, in his early career. His first graduate student was Sally Ride, the first female astronaut.
Yeah.
Yeah, so she was his first. I was his last. He passed away right after I graduated.
Wow. Chat, let's talk Sally Ride when you get a chance. Hakeem, I want to come back to the hardware, because, again, we're talking about building stuff, right? And we have this thing about... it's the engineering design process, right? And really, it's been described in a number of different forms. I think we like to talk about it in a matter of, like, where you start off with, you're dreaming something. After you dream it, you need to plan how you do it, and then you create it. And then, much like science, you test it or go through experiments, which we all know a lot about in engineering. And then in your experiments, you're going to get your results and improve it. And then you launch it, right? You launch it, right? I know you worked on a number of things, but what can you tell us about this particular hardware, again, that we started to talk about?
Yeah, so we would fly 16 to 22 telescopes at a time. So what you see here is an array of telescopes, and each one is able to image the sun at a different temperature. But that relies on the optics only allowing in a narrow sliver of light. So what happened is 3 engineers separately created technologies that Art Walker and his graduate student before me, Joachim Lindblom, recognized. So the first one is, there is the light that is the most difficult in the world to work with. It's called extreme ultraviolet light. All right, it's from wavelengths. Yeah. Okay. So
super small wavelengths, very high frequencies. Is that?
Exactly. Right. And it is, just before X-rays is extreme ultraviolet.
Okay, got it.
And the thing about extreme ultraviolet light is that it interacts incredibly strongly with all matter. So it doesn't make it through, so basically, if you have the slightest film of anything on the surface of your mirror, it ain't coming out. Wow. But basically, this guy, Troy Barbie, created EUV multi-layer optics, which are now in EUV lithography machines. But we were the first to work on it. Another guy named Spiller created ultra smooth mirror substrates, because if the light has this little tiny wavelength, the surface variations have to be much smaller.
Right.
So you put the multi-layer on the smooth substrate. And then there was Forbes Powell up in Seattle, Washington, who had these thin foil filters, because the light that we wish to reach our mirrors, the visible light on the sun is 10 billion times stronger, right? More intense. Yeah. So you got to block that light out, but you got to let through this light that basically can't get through anything. So here's how my very first papers were: model these mirrors and these filters, model them, and see how they will interface with the solar spectrum. So first I had to create the pass bands for the optics based on mirrors, however many reflections based on filters. Right. Then I had to convolve it with the solar spectrum. Then it became, they send us the mirrors, right? And we go to Stanford Synchrotron Radiation Laboratory, and in our vacuum chamber, right?
And see how it
absorption pumps.
Yeah.
You start off with your standard carbon vein pump, then you go to your absorption pump, then you go to your helium cryo pump, and then you bounce light off of it, and I use channeltron detectors and photodiodes, and then you get your flight hardware, right? Once you go through the process of going back and forth to manufacturing, right? Now we narrowed it in, because if you're off by just a little bit, you're getting nothing in your images, right? And so then it becomes time for assembly. Now you see this thing, it has hundreds of parts. Art Walker took me into a lab room, and it was boxes of parts in bags. No diagram of the entire art would sit on his drafting table every day. I had no idea what he was doing.
Yeah.
But he's like, assemble it. So in the summer of 1994, I spent the whole summer piecing together this jigsaw puzzle with no idea. Mind you, having to maintain cleanliness, it was just, it was like 8 a.m. to 7 p.m. every day in the damn clean room.
Yeah.
Then it's go to White Sands Missile Range, take it through all of those tests, right? Focusing, and coming up with how am I going to focus my mirrors? How am I going to, man, it is so detailed. But then the cool thing happens. It's time for launch. Right. You launch that sucker, and then after it launches and you get the data, helicopters come in, pick you up, take you down the range to where you pick up your payload and then bring it back. And then you sweat, because we were the last space experiment to use photographic film as the detector. So now getting those film canisters and developing that film was done by Richard Hoover, who is always on the show Ancient Aliens these days, by the way, for the last several years, because he also studies diatoms.
Okay.
But Richard was, if anybody out there is in the satellites, there was a series of satellites called OSO that were sent up, and Richard was the expert on photographic film. So he's the guy who was in charge of that. Then you had to digitize the data. Right? So we had to go to Mars Space Flight Center because it was film negatives, right? Yep. Digitize it. Then you got to calibrate it. You got to take those same mirrors back into the lab, same filters and the film, because you want to say darkness on this black and white film corresponds to this particular amount of energy striking the focal plane, which you can then translate to knowing the reflectivity of your mirrors, the throughputs of your filters. This is how much energy left the sun at that location, right? And then you now have data that you can put into your models to try to get some science out.
To make your models even better. I'm not even gonna lie to you, Dr. O. That sounds like a lot of dependence on accuracy, paying attention, right? You got to really be paying attention to the details. And I see a question that was on the screen for a while, and I'm gonna ask you in just a second, but you almost gave me a flashback. And I want everybody who is watching on YouTube, on Facebook, shout out to our building committee that's been here for a while. On Twitch, we go almost every day, and we're building models. And when I heard you talk about how you had to put all these different components together without instructions, I sort of have flashback to our last building day here on the channel. So again, we do a lot of that here on the channel. I want you to know about that.
Wait a minute, you actually build live on your channel?
We are building stuff with NOVA. That's what this channel is all about.
Wow.
That's what this platform is all about. And super happy to have you here. But here's a question that came from Tariq Kelly on Facebook. They said, I'm interested in tired light theory, but I don't know where to start. Any tips? Does that ring a bell? Tired light theory.
Yeah, skip it. So here's the deal. All right. So what we know is, we can measure the spectra of different elements in the laboratory. And we know, for example, Lyman alpha is at 1,216 angstroms. We know, helium 10830, right? We know the wavelengths at which these atomic transitions occur, right? So the wavelength of light is related to the structure of the atom, right? The electrons move from one energy level to another. Right. That gives you a well-defined energy. But when we look at more distant galaxies, we see that entire spectrum, which is a series of lines like a barcode, is shifted to longer wavelengths and spread out. It's as if every wavelength was multiplied by the same number, all right? Okay. So there were two theories in the 20th century of what's happening here. Is it that somehow, as light is moving through intergalactic space, it's getting the energy sucked out of it? That's called the tired light theory. Okay. Or is it the case that as it's traveling through intergalactic space, space is expanding and the light gets stretched by the exact same amount that space expanded while the light was traveling through it? The answer is the latter, because it's as if, so if I see a spectrum and I see that every wavelength has been multiplied by 3, then I know that the universe today is 3 times bigger than it was when it left that object, right?
So got you.
Yeah. And so if you think about it, I give this example of a rubber band. So the key thing that lets you know that it's being stretched and not energy sucked out is the fact that it's proportional to distance. Something twice as far away will have the light stretched twice as much. Something 3 times farther away will have it stretched 3 times as much. So if you think about a rubber band, if it's 1 meter And in 1 second, I stretch it so it's 2 meters. If you're at this end, you see the opposite end move away at 1 meter a second. You see the center move away at 0.5 meter per second. And you see this piece where you're holding it don't even move at all, really, relative, right?
Yeah,
Yeah, so it's proportional to distance. So that's the stretching. Yeah, so tired light is sort of like an idea that came through and it was competitive for a while, then it stopped being competitive.
That's why. Okay, cool. And I'm going to see if I got another question. I have some more hardware I want to ask you about, but there were a few other questions that popped on the screen. Let's see if we can get them up here, or we maybe just circle back to them, because a lot of people are getting light bulbs go off. Let's see.
I bet.
Let's see. They say, is this the Chandra X-ray Observatory or relay that he's talking about? Chandra X-ray Observatory. I wonder if there's a way.
No, it's related in the following way.
Okay.
Prior to the invention of this multi-layer technology on mirrors, which allowed you to have normal interface mirrors, just like a regular telescope, the only way that you could reflect extreme ultraviolet and X-ray light was via grazing incidence mirrors. So that's like skipping a rock off the pond. So here's what I mean. A lot of mirror figures are based on geometry. Okay. So if I have a normal mirror, I take a parabola and I cut the bottom off. So it's like the bottom of the parabola right here, right? Yeah, that looks like a mirror that focuses all the light, but a grazing incidence mirror takes this section of the parabola, right? Up here, where it's almost straight. So instead of the light coming in and bouncing like this, the light bounces like that, right? And so the Chandra, in order to be so dope and amazing and to gather enough light, is a bunch of nested grazing incidence mirrors that are really big. Because if you think about it, if I'm coming in normal incidence, all of this is my collecting area. But if I'm coming in like that, it's just a tiny little collecting area. So most of the light you're not actually collecting. So you just need a lot of surfaces to bounce it off of. So this is the follow-on technology. So what they're doing now is combining the two. For very high energy X-rays, you have a multi-layer grazing incidence, which is, pretty cool. Engineers are clever.
Yeah. We are. Thank you, Dr. O. I'll take that. We are pretty clever, I must say, even though I don't have anything to do with this particular technology. But here's what I want to ask you. These are great questions. Again, YouTube, Facebook, Twitch, everyone, welcome to the Building Committee, Building Stuff with Nova. Keep them coming. I know about this particular program that you also worked. Again, that's an astrophysicist. You have a lot of engineering experience. And so you worked in this project called, what is the Supernova? It was
Acceleration Probe.
What is it? SNAP. What is it?
Yeah, the Supernova Acceleration Probe satellite. Which is more,
probe. There we go. There we go. And you worked on basically being able to, I guess the purpose of it, and you can tell me a little more about it, was about exploring dark energy.
Yep, dark energy. And it had a dark matter component because, you actually wanted to get funded, so you have to make it do more than one thing.
Yep.
So in fact, the idea that it morphed into, so essentially, the guy who led the team that discovered dark energy, Saul Perlmutter, him and my postdoc advisor, Mike Levy, they proposed this. And so the Department of Energy was funding it. And so then, when you start bringing in bigger, parts of the government, NASA, and you're talking about $1 billion satellite, you need congressional committee approval. Right. The East Coast scientists who also discovered dark energy were like, no, we can do it differently and better.
Right. We went in like, hold on, don't skip over us. Yeah.
Exactly. Right. So it became a competition. So eventually they decided to come up with this thing called the Joint Dark Energy Mission. And ultimately it ended up becoming what is now known as the Nancy Grace Roman telescope, which is, a wide field observing platform. But it's also now, while all of this is going on, exoplanets took off. So they're like, let's study dark energy, dark matter, and exoplanets. just like with Webb telescope. You gotta add an exoplanet.
Let's make it a multi-purpose mission at this point, right? Program.
That's right.
Well, here's what I want to show, because I think a part of this, there was the development of some detectors, right?
That's right. Yeah.
And I know up to this point. Yeah, go ahead, break this down.
Yeah. So if you look right there, what you see is this is what the desire was, to be able to fully tile a focal plane with no gaps between the chips. So if you go to the one where I show those two focal planes, the next slide. Yeah, you'll see like these large cameras, because the chip needs both mechanical and electrical interface. On the one on the left, the CHT Megacam, you see those spaces where the connectors are. And then for XMM Newton, which is an X-ray one, they put them in different planes in order to, so
they weren't
it's
together.
not ideal.
They weren't like touching each other, basically.
Yeah. All the way around. You want to be able to tile it like you tile your floor, right? Where there's no gaps.
Right, yeah.
And that way you get the data that reaches the precision that you need. So if you go to the next two slides, you'll see what they got, where they actually got. So that was my design, right? That was the very first four-side buttable.
This is the four-sided.
Yep. So everything is coming out the back. So there's the electrical connector right there, and there are the alignment pins, and there's the mechanical interface there. Mm-hmm. And so when I say everything is done in teams. So I work with John Berkovich, Armin Karcher, and another dude. I can't remember his name. Starts with an H. But we work together, me and 3 engineers, right? All right. And so if you go to the next slide, you see where they've been deployed now. So this is the dark energy camera down in Chile for the dark energy survey. And the next one is America's next big ground-based observatory, the Vera C. Rubin telescope. And so they're going in there. So my work, I did the pioneering work. And then, of course, iteratively has been upgraded, and so I actually work on metrology for deploying the so-called tower rafts at Brookhaven National Lab with my students in preparation for this as well. So building focal planes, calibrating, designing, testing, that's,
Yeah. I think you said the word that we want to make sure we get clarity to. Metrology, that's metrology, did I say it right? That's basically the process of
metrology.
How to measure, right? The ability to measure, right?
With incredibly high precision, right? Because here's what happens, right? One of the sciences that we do to understand dark matter is called weak lensing. So if you look at a galaxy cluster, around it, it acts like a big gravitational lens. So there's a trend. If you just look at the photograph, you might not notice anything weird about the galaxies. But if you do a detailed study of their shapes, then what you'll find is that there are trends in their shapes, and that reveals the presence of dark matter. So you need to be able to measure their shapes to incredible precision. But remember, you have a mechanical interface, you have an electrical substrate like an aluminum nitride circuit board or something, and then you have your silicon chip. And you cool all that stuff down to liquid nitrogen temperatures. Wow. So they're gonna shrink differentially, and you have tolerances on how much they can actually warp, and you still get your science out, right?
Yeah, exactly. Yeah.
Yeah. So you got to measure that. You got to measure it when it's flat. You got to measure it when it's warped. So the paper where I developed the packaging, we did all that. And then, if you're going to use them in space, you got to take it into a vacuum chamber and see what comes out of that thing. Because you have different adhesives holding it together. You don't want stuff to come out of there in space, outgas, and then get on the surface of the detector. There's,
so many things can go wrong. Which is why why the engineering design process is iterative. Like, we like to, again, remind folks that you continue, you test, improve, and then after you get your results back, you say, okay, how can we make it better? Then you test that, and you continue to go through this process. And because at the end of the day, science is at stake, right, Dr. O? Science.
You got to take it into a lab and irradiate it to see how the space radiation is going to affect it.
Right.
Yeah. And then you're building your ASICs.
What's this right here? This is
is the dark energy cameras. That is for the Vera Rubin telescopes. Focal plane right there, right? So the detectors that I worked on, these deep depletion devices, so they were invented by a guy named John Holland, and then most of the work of the early development was a team. And so, there were these two guys, Bill Colby and Armin Karcher, engineers that were always there. And then, I was one of several postdocs who would come in and contribute to the project, right? And, so I just happened to be there early as they first started coming out, and they were trying to get them to go from research to development, get it out the door. And because I came in from industry, from Silicon Valley, I was able to do that. So I was able to get a 2K by 4K, deliver it to UC Santa Cruz to deliver it on Keck. And, also in this instrument called the Supernova Integral Field Spectrograph on Keck.
Man. chat, in case you all didn't know, we have an astrophysicist that just happens to know a lot about engineering, I must say, that has an experience in Silicon Valley.
I'm a hardware guy.
You're a hardware
guy, man.
You're a star hacker. You use your understanding of the stars and what's happening out here in space, particularly at the core of stars, right? In some sense, is that?
Well, surfaces
Okay,
of
so
stars.
at the surface of stars. Yeah. But you're using that to then help create models and ultimately create hardware for how we can detect it.
Yeah.
How we can measure it.
Like there's like biomimetic technologies. I do astromimetic technologies.
Yeah.
So, in Silicon Valley, my knowledge of reading light, which I learned from stars, is directly applicable. And, one of the greatest things, delights of my career, I'm one of those people that like to see other people succeed.
Yeah,
but, we're all on a team.
Yep.
So we all have a role to play. But one of my graduate students, so I told my graduate students, I would tell them about my success in Silicon Valley, and I would say, listen, pay attention to areas that are adjacent to what we do.
Yeah.
You might find that you have an application that they hadn't thought of. So my graduate students, Dave Chesney and Bryce Orange, led by Dave, said, hey, Dr. O, I found this process that I think that happens at the surface of the sun. I had them looking at what are called scale invariant, self-similar processes. Okay. And he's like, there's a type of reconnection that happens at the pole of the sun that drives these jets. It also happens on the scales of millions of miles. It also happens in planetary magnetospheres on the scales of miles, and in the cores of galaxies on the scales of light years. If we can make it happen at a scale of 1 meter, we will have the world's fastest ion propulsion technology.
Man, all right. So we're gonna talk about ion propulsion technology, but I want to let chat get some of this. Shout out to YouTube, Facebook, Twitch. Yeah. Everybody's with us. Let's see if we can answer a few more questions, because you touched on ion propulsion technology, which I think ties into something we've been doing here on the channel around rocket science. We start playing this new game. I'm gonna tell you about it in a second. But let's see if we got anyway. Shout out to Terra Blazer. We see you. Shout out to everybody that's commenting again on YouTube. We see you on Facebook. Do we have any questions, team, that we want to go ahead and answer real quick? Because I'm dying to start asking them about ion propulsion technology. That's definitely what we're going to get into here in just a second. And I'm going to set it up for you, too, before I see if there's any question, before I keep it moving totally. But we've been playing this game. So Twitch, again, everybody who's watching on different platforms, know that we're over on Twitch. And one of the things we do is we do a lot of gameplay, like, video games. And there's this game that we started that I'm going to pick up later on this Friday, actually collabing with another creator on Twitch, called Kerbal Space Program. And the whole game, Dr. O, is to create rockets to ultimately, launch them, go into low Earth orbit, go to the moon, so much for it. And it's gamified. It's really fun, right? But so far...
Wait, y'all actually launch it?
Say what?
Y'all actually doing little rocket launches?
Yeah, rocket launches with little green people, right? We're sending them out to space. It's pretty fun. I love those. But so far, right, before I even learned about this ion propulsion, we were been exposed to solid fuel rockets and liquid fuel rockets, right? Solid fuel rockets mean you have this fuel. Obviously, once you light it, it burns up, it's done, right? Liquid fuel rockets is more of a chemical combustion. You mix two different types of, oxidizer and a fuel, and you get this propulsion, right? But you brought up ion propulsion technology, which I'm going to get you to explain right after I ask this question that I see from somebody in the chat. It says, is the new sun cycle surprising scientists? I'm going to come back to the propulsion, but let me ask this question. I want to make sure they get in. Go ahead.
Oh, yeah, it is. If you look at the solar cycle, and the best way of measuring the solar cycle, or the easiest, is just to count the number of sunspots, right? And it's an 11-year cycle of the sunspot number increasing and decreasing, going from between solar maximum and solar minimum. And over the last several solar cycles, the minima were getting smaller, the maxima were getting smaller and smaller. And during quiet sun, there were times where there were no sunspots. And we thought that we were going into another situation like in the 17th century, the Maunder minimum, where there was this long period of no sunspots. And coincidentally, Earth went into the little ice age. And I say coincidentally because we don't know.
Right.
You can't draw a direct causal relationship, but it's suggestive. And so we thought it was going down, but no, it came back up. It's doing. Yeah, if you go up back to that sun slide you were just on, that's the slide you want to be at when we start talking about ion propulsion. That one. Yeah.
Okay. By the way, you just educated me, and shout out to that comment chat. I didn't know about new sun cycles, and so I just got a bonus piece of information here on the stream. Thank you for answering that, Dr. O. But now you're about to break down for us this whole idea of ion
Hey, click that photograph. Click that photograph. The one right there with the sun. Click it. It's a movie. Let's see if it works. Ooh. There we go. So if you see those jets shooting off there, this is a negative, right? So what you see dark is really bright. What you see bright is really dark. Yeah, you see these jets shooting off? Yeah. So if you go to the next slide, one at a time, you see the model of what that looks like. And so if you see, you have this dome-shaped structure, and you have this thing called a spine. Mm-hmm. So those lines represent magnetic fields. And so the spine is where the magnetic field goes to zero. Go to the next slide.
Yeah.
So if you zero in, you have what's called a fan spine geometry, right? So this is what the sun is doing. It has the null point, the spine is where the magnetic field goes to zero, and either all the magnetic fields can point in or they can point out. But that thing right there is what stores the energy that you can then release. But you have to perturb it with a different magnetic field. And so if you're thinking about how the hell do I make this thing, you ask yourself, how do I create that particular magnetic geometry in the lab? It's not, so basically the PhD, half of the PhD dissertation of Dave Chesney was actually modeling it, right? So we had to go through and just run all these different, you basically have a matrix of the magnetic field elements. And you basically have to go through and find every solution to, it's one of these problems where you basically are exploring a parameter space, right? You're exploring parameter space and finding the solutions that fit your thing. So if we go to the next slide, you see here is one of the things that were built in the lab.
This is a physical model right here. This is a physical model.
Physical model.
Okay.
Yep, and so you can't see the magnetic field, obviously, but that is just one. We have three different configurations that make that. Now, if you go to the next slide, now how do you perturb it? So here, what you see is the left panel, you see a circle. So that's like you're looking, the spine is coming straight out of that circle, right? And then to the side there is you're looking edge on. So the left side, you're looking like this side, you're looking like that. So that circle is the second magnetic field. That's the perturbing field. And what it does is it squeezes. As you go from time 0 to time 3, it squeezes down. And what you see on the right side is the current of the jet shooting out at the bottom, right? So first it goes, and then zoom, right? So you have the
almost
field.
Like collapses on itself and then shoots out. And these are two different views, top view and like side view, I guess.
3,000 kilometers per second.
That's crazy.
Vasimir ion propulsion gets 60 kilometers per second. This is 50 times faster. So go to the next slide. So how do you create that magnetic field that squeezes down? Turns out people way back in the mid 20th century who were studying fusion created this device called a dense plasma focus. What you have here is a circle of electrodes and a central electrode. The outer ones are opposite polarity of the central one. You connect this thing to a big capacitor bank. You have a glass dielectric at the base, and when you boom, set up off that charge off of those capacitors. If it's inside of a rarefied gas, it ionizes that gas, creates that plasma, whatever the hell you call that thing.
The green stuff.
Moves to the end and squeezes down so hard, it literally creates fusion. You don't get more energy out than you put in, but for us, that gives us exactly the magnetic field that we need. Now, if you go to the next one, you'll see it's also not vaporware. It should look like a blank slide. Hit it. Yeah, and that's the actual DPF firing in the lab.
Oh man, did you take this, or was this from another lab?
Dave and Bryce. So so basically, I left after they graduated. I left the university, and they formed a company, and they've continued development. So I still work with them up until 2017. Even though I left the university in 2014.
Yeah. So man, there's so much I want to ask you, and like I'm gonna say the fact that we both, just side note, we both were at the same university within a year of each other. I attended the university the year after you left university there in the University of Alabama, Huntsville. And
oh, no way. I remember that now. Yeah.
And a lot of those things but here's the thing I want to bring up, because I have a couple more questions. Chat, if you don't know, this is Dr. Hakeem Oluseyi, a.k.a. Dr. O. I'm Dr. Nehemiah Mabry, a.k.a. Dr. Need. This is Nova Building Stuff. If you're just joining us on YouTube, Facebook, we hang out on Twitch as well on a daily basis where we're building stuff together. I am your mentor, sometimes your mentee, your colleague, your personal guide. We're just hanging out, building stuff together, and you are telling us, Dr. O, about how you were involved in so much hardware that you applied your star hacking knowledge to allow people to innovate, and also has led to several patents. And here's what I want to quickly get you to touch on really quick. If you can, talk about fusion, because obviously we're at a point where we're starting to get to, I guess, sort of a net positive energy that's very
it's been
clean.
achieved.
Yeah, right? Talk about fusion, where you think that's going. We don't stay along, but I just love to get your thoughts on fusion since you mentioned it here.
Yeah. Man, I think fusion, once we achieve net positive energy output in fusion, which, I'm a Missouri dude. I'm not from Missouri, but, I take on that. You got to show me, right? Yeah. It's like, okay, experimentally it's possible, but until you've done it, it ain't happened, right? And so now it's happened. And then we got the tokamak reactors. So let's just assume that the, have the two types, the laser pellet technology that they're doing at the,
you kind of bombarded with like a bunch of
so basically you put it into this metal capsule and you bombard the capsule with the lasers. That creates X-rays which bombard the pellet,
right?
And that causes the outer layers of the pellet to shoot outwards, which cause the inner things to go inwards,
right,
and you get that energy out. But that facility is an experimental facility.
Okay.
It is not designed to give you fusion electricity out.
Right.
right. So in order to do that, and the same thing with the tokamaks. If you look at a tokamak, you have ITER or ITER, as some people call it. They're big, giant, hundreds of tons machines, right?
Okay.
And all of this stuff has to be engineered to be more efficient. There's like net energy out as far as like I get more energy out the pellet than I put into the pellet.
Right.
But that doesn't mean I get more energy out of my building.
Right.
That's what
it still took a lot of energy to. Yeah. All right. I got you.
All the energy don't go in the pellet. Right. There's a lot of energy going in the building that doesn't end up in the pellet.
Gotcha.
And so in order to get that out, and then you have to turn that energy into something that's going to turn a turbine. Right. So, you have all these places.
Yeah.
And I think with tokamaks, the issue is they're just so damn massive, because the thing that I see is that what you want to have the ability to do as a species, of course we want to move away from fossil fuels, but we also want to be able to have electricity in places that are, say, mines, farms, in the middle of nowhere.
Yeah.
Right.
Yeah.
Basically.
Yeah.
And so that means that you're going to have to miniaturize it. And then there's fission technologies like thorium salts and these sort of things. Right.
Yeah.
Yeah. And so, I think there is a bright future, pun intended. I crack me up, nerds, and my fellow nerds and geeks.
I love it.
Yeah, man, I think that there's a bright future, and it's a matter of engineering our way there.
Yeah.
And of course, engineering costs money. Right. So that at this type of money, that requires political will, right? And so this is the future of humanity. And I mean that in a big way. When I complete my next book, I talked to you a little bit about that in Boston, about how we're going to be building our own stars. So, yeah.
Man, listen, in other words, chat, to my building committee on YouTube, Facebook, and Twitch, there's a lot of work for us to do here at Building Stuff at Nova. We got a lot of engineering to accomplish. And you know what's funny? Just a quick nod to your podcast. You're a podcaster. You have a show, Does It Fly? Shout out to your co-host, Tamara. And I know a recent episode you all talked about Iron Man, the technology in Iron Man, and how he had the arc reactor in his chest. What you're telling me, though, is real arc reactors are nowhere near the size that Iron Man or Tony Stark had in his chest. We got a long way to go before they're that small.
Yeah, maybe he hooked up with Doctor Strange. He put some mystical energy in that, but that ain't, Yeah, I don't know what they're doing. How that's not that cold fusion action. I don't.
You know what I'm saying? A little bit of sci-fi, action. So shout out to your podcast.
A little bit of sci-fi.
Yeah, everything you're doing. You all check them out. Dr. O It's all over the internet.
Love it, Nate.
Incredible story, incredible insight. I have one more thing I want to tell you about and get your thoughts on. Now, again, for those who are joining us, this is Building Stuff with Nova. This is a platform we've been doing for several weeks now. We're going all the way to the fall where we have a finale, a season finale, Dr. O, that will be a 4-day engineering-themed escape room. It's going to be awesome.
Ooh.
Yeah.
You got to build something to get out?
Listen, we're going to build something, and you not only do you got to get out, you got to exemplify, or those who will come in person, as well as our online audience. So you all hang out with us. You're going to have to exemplify the knowledge and the execution of engineering principles to get out. So it ain't just like, it's not your normal escape room. We're talking about something high tech here, right? And here's the theme, though, and I want to get your thoughts on it again. We are looking at this being set in the year or right before the year Y3K.
Ooh.
Y3K.
Okay.
And one of the motifs that we see now, right, not too far after Y2K, is that we're not so much software. It's a lot of AI, right, online. And so sort of the framework of the story is that at right before Y3K, we realized that we kind of made a similar mistake in that AI needs to now be retrained through a lot of the things that at that point in time we're fully dependent upon it on. So you're talking about your structural system, your mechanical systems, your energy systems, your computer system, all of that, right? And so that's sort of what we're sitting through. And so I just want to throw out to you, chat, if you all don't know, we're going to be having another ideation session about this tomorrow with our friends from Trapology Boston who's putting this together. But since I have you, Dr. O, I want to get an idea of what do you think the Y3K, the year of Y3K might hold as it relates to your field. Obviously, if we're in a situation where we have to retrain AI that we're going to do in these escape rooms, we're going to have to go back and make sure we understand everything we built it with. But from your standpoint and the things that you're interested in, how do you envision a year Y3K? Maybe we can incorporate a little whatever you share into our escape room.
Life elsewhere has been discovered. I'm interested to understand. So I was looking at something recently about how humans are going to evolve in the future. And one of the things they were saying is that such a high percentage of people now date via online apps that it's all based on looks, right?
True.
So we're going to become a very symmetric looking
we're going to be a beautiful people, or we're going to be bored of how we look at it. One of the two, right?
Right, yeah. Everyone is so symmetric. Symmetry is beauty, right? It's kind of what they claim.
Perfectly congruent.
Perfectly congruent, yeah. Now, here's the question. So, I love to study deep history. I love, whether it's the planet, humanity, the universe. And one of the things that's really interesting to me is how over the 2 million years of Homo erectus's existence, brain volume doubled.
Oh,
all right.
Wow.
And, it went from like 600 cc's to 1,200 or something like that, right? And then Homo sapiens comes around, and we have these superpowers, brain superpowers, but our brain has begun to shrink a bit in recent times, right? And so I'm wondering, there's not just body plan evolution that is occurring. There's also brain evolution. And so I'm wondering how these interfaces, things like AI, how that's going to drive future brain evolution. I have no idea, but it's interesting to me what the question is, because I don't think you could have foreseen it, right? I don't think, as the brain adds these layers, I don't think that would have been predictable by Australopithecine scientists.
Yeah. Well, listen, if indication that I can no longer remember phone numbers or go anywhere without a GPS, it's anything that indicates, you know what I mean? Like, maybe I can only imagine how dependent we could be, especially if we continue to program and develop these algorithms that do stuff for us.
Yeah.
But one thing's for sure, shout out to everybody in the chat. I want y'all to drop some emojis. I'm sorry I couldn't get to all the questions. We had a lot of great questions, but man, I feel like this should have been like a 4-hour stream, to be honest with you. Like, Dr. O, you brought so much great knowledge. I just really can't wait to have another conversation with you on or offline,
Absolutely.
To be honest with you.
Thank you, mentor.
No, I think it was the other way around. Y'all show some love
Dr. D.
to Dr. O, who's joined us here on Building
Thank
Stuff with Nova. This has been a fantastic interview. Y'all, make sure you come back to continue to hang out with us. Sometimes we're going to be streaming on YouTube. Sometimes we're going to be streaming on Facebook. But most of the time, if not all the time, every day, if you will, we're going to be on Twitch. So make sure you hang out with us on Building Stuff with Nova. Come back tomorrow. We're going to do more ideation, and we're going to see if we can I don't know, consider what Dr. O shared with us about sort of our brain sizes in the year of Y3K into our escape room. But until then, you all continue to keep building, and I will catch you later right here on Building Stuff with Nova. Take care. Peace.
Peace. Now I got to talk about the technology of Goldfinger.